a comparison of means using students T. And we're going to do this in 3 different applications. The first is comparing a set of experimental data to a known value. So this would be similar to comparing some experimental data to a reference standard. So let's assume that the truth is 7.2. You purchase a known sample and it tells you that the concentration of element A is 7.2. You then go into the lab and your data indicates that the concentration is 6.7, 7, 6.9, and 6.8. And you want to know whether or not your data agrees with the truth. So I've plotted the data over in this plot, and the blue triangles would be your data, and the truth is the red point. And it looks like the blue data are all too low. The question is this variability sufficiently large that within a 95% confidence interval, the truth would be contained within the uncertainty of your data? And that's what the T statistic gives you. So remember that the confidence interval, mu, is x bar plus or minus T, the T statistic, with the probability that you assign, the standard deviation, and this would be the sample standard deviation, divided by the square root of n, which is the number of data points. So I can calculate this interval. So let's see how I do this in Excel. I click on the mean, and the mean is simply the average of C7 over C10. So that's my experimental data. The standard deviation is C7 over C10. And the T statistic, instead of looking it up, I'm going to use the Excel function T inverse. 0.05 says that I want the 95% confidence interval. So it's 1 minus the confidence interval, 0.05. And 3 is n minus 1, or the degrees of freedom. So my confidence interval is 3.2. So I can now go in and plug in the mean plus, so this is x bar plus the T statistic times the standard deviation divided by the square root of n. And I can do x bar minus the T statistics times S divided by the square root of n. So the confidence interval for this data at the 95% confidence level is from 7.06 to 6.64. So those are the pluses. So that you can see the truth is well outside my confidence interval, and it is reasonable to conclude that the results are different. Now, another way to do this is to calculate T Calc. And notice T Calc is just the reorganization of this equation. What you're calculating is what would the T statistic have to be so that these intervals include the truth. Okay, so it's mu minus x bar divided by the standard deviation times the square root of n. And in this case, so I'm going to take the absolute value of C4 minus C12, that's mu minus, that's the population mean minus the sample mean, divided by the square root, divided by, the standard deviation times the square root of, in this case, 4. And, and then you do a comparison. And if T Calc is greater than T, the results are different. And sure enough, T Calc is 5.42 and T is 3.18, so they are different. Now, if, on the other hand, I had made another measurement and my measurement was 7.6, now you'll notice I put a point out here. My data is not as good, but at this point, T Calc is less than T statistic, and the results are the same, or at least we can't conclude they are different. Now, my data is worse, but in this case, it looks like they could overlap with the truth. Edit, undo. So that's comparing a series of replicate measurements to one point, which we'll call the truth. Second case, we're going to compare 2 data sets, the circles and the squares. And data A is the circles and data B is the squares. And so the T calculated for this comparison, so now we're going to jump right to calculating the calculated T statistic, and we're going to do a comparison. The T calculated is X bar 1 minus X bar 2, so the standard deviation of data set 1 minus the standard deviation of data set 2, take the absolute value of that, divided by the pooled standard deviation, scaled by the number of observations in both data set 1 and data set 2. So how do I implement this? I take the average, B1 over B8. I take the average of C8 over C11. I calculate the standard deviation for both data sets. I've listed n for both data sets just to help me in subsequent calculations. N minus 1 is the degrees of freedom. And here is my S pooled. S pooled is right here. And it is the square root of the variance of data set 1. So it's the standard deviation squared. Times B16, which is n minus 1. So that's this right here. It is the standard deviation squared of data set 2 times n2 minus 1, and the whole thing divided by n1 plus n2 minus 2. So notice that my pooled standard deviation is somewhere in between the two standard deviations of my data sets. And T Calc is right here, the absolute value of X bar 1 minus X bar 2 divided by the pooled standard deviation times the square root of n1, n2 over n1 plus n2. So 5.8 is bigger than the T table, 0.05. And in this case, you use the degrees of freedom of all the data. So it's going to be B15 plus C15 minus 2. T table's 2.4, T calc is 5.8, so we can conclude they're different. And that makes sense. Now, if you went ahead and you changed one of these data points, let's take the low one and change the 6.9 to an 8. All right, now we got 3 points and it overlaps. T calc is less than T table, and you would conclude that they are not different. Go back. The final T application of the T statistic that we would like to talk about is pairs of data. And this is typical with the data set we collected on the boat last week when we went out and made temperature measurements, and we want to compare them to the buoy. So here I have Z, which would be depth in meters, temperature measured with sensor 1, temperature measured with sensor 2. In this case, we're going to calculate the standard deviations of the deviations in the data. So D in this case is simply the difference between these two. So, and I'm going to use the T calc is going to be the average deviation of the two data sets divided by the standard deviation of the deviations times the square root of n. So, average deviation is simply the average of all of my data. The standard deviation is simply the standard deviation of the differences in my data. And T calc is now the absolute value of B26 divided by D27 times 21 to the half. And there are 21 measurements, so that is n in this case is 21. T table is T inverse 0.5 and 19, it's degrees of freedom, so it's n minus 1. You don't count, it's the numbers of pairs of data you're comparing, because you're really only comparing the D's. So you have 20 observations, minus 1 is 19. So 37 is clearly bigger than 2. They are very different. And if you look at the data, they have the right shape, but there is clearly a systematic offset between these two data points. Now here's the interesting thing about statistics. Let's assume the 19-meter sample, instead of being a temperature of 10.3, was 30. Now we have a point way out here. This data doesn't look nearly as good. You'd say there's something going on with the blue data, but now you would conclude that the two data sets are the same. Or at least you couldn't conclude that they are different. So you've got to be careful in doing these comparisons, because this bad data point basically means that the blue data has significant scatter in it, and that scatter now encompasses the red data and allows you to conclude that the two data sets are not different, even though your eye and your brain probably tells you that they clearly are. And in this case, you would probably throw out the 19-meter sample, and at which point the two data sets, again, would be different. So be careful in how you interpret your data. Don't just use the numbers. Look at the data, think about it, and then come to your conclusions.